molecules. I will point out some cannot be used to make those glucose molecules. I'm also just pointing out right now that molecules that are involved in controlling either this enzyme or the last one, the other control point, which is phosphatidylkinase, makes sense. ATP slows both these guys down. AMP increases their activity. Citrate decreases their activity. Where would the citrate come from? Citric acid and citrate are related to each other? Guys, what is citrate? The conjugate base form of citric acid. I make that in the citric acid cycle, and if I've got lots of that taking place, glycolysis is going to shut down. On Biochem 2, I'll come back to this thing. That's kind of important. One of the ways that some people are trying to reduce fat production. Not important right this very second. I will also tell you a little bit more about this, especially in Biochem 2. Both this enzyme and phosphatidylkinase are controlled by the activity of various hormones. Insulin kind of tends to promote their activity in liver. Glucagon promotes their activity inside muscle cells, also kind of can shut them down in some circumstances too. And most of that control is by putting phosphate groups on or taking them off, making molecules either more active or less active, all right? It's changing their structures, changing their ability to do what they're supposed to be doing, all right? The other thing I can tell you about, again, don't memorize this sheet right here. Just look at it and ask yourself, why would these molecules shut this down? And notice that these guys that shut this thing down or turn it on do the opposite for the reverse processes of gluconeogenesis. What shuts this down turns this on. What turns this on shuts these guys down, because you don't want both processes taking place inside any one cell. All right? The Cori cycle is the combination. I'm not going to go through details on it. The Cori cycle is the combination of glycolysis in the muscle, gluconeogenesis in the liver. It costs you basically 4 high-energy phosphates. Glucose goes this way. Again, we're doing this lactate, as Kyle pointed out, and as Colin pointed out last week too, or the other day, to regenerate the NAD plus molecules to keep this process going. That NADH that's made here is used in this process. Basically, all this is doing right here is reducing the oxidative stress in muscle cells, putting it in the liver for short periods of time. Glycolysis, gluconeogenesis. All right? Everybody look at glycogen for a second. Do you see any phosphates on it? Is that important? Yes. How do I go about making glycogen? These words should not be on this slide. I just copied the picture, put glycogen synthase from someplace else. All right. On that picture I showed you like this before, I completely ignored this spot. We are now talking about this part, right? If I'm going to make glucose molecules into glycogen, again, are there any phosphate present here? The answer is no. But I'm going to need some energy. Why would that be? Because when I take little molecules and make them into big molecules by polymerization, it takes some kind of energy, all right? Exactly how much? Pay attention. I take a glucose molecule, I phosphorylate to make it glucose 6-phosphate. This is reaction 1 on your cheat sheets. I can take a glucose 6-phosphate molecule and make it into glucose 1-phosphate. That cost me energy? Nope, it's exactly the same as reaction 8, as Colin pointed out the other day, or somebody pointed out over here, all right? I'm simply moving the phosphate group. Why do I go about doing it? Where? Oh, that's on my cheat sheet. That's reaction 14, something like that. That sound right? Doesn't cost me any energy. This guy reacts with this guy to make this guy. Does that cost me anything? Does it cost me an ATP? What do you say, Jackson?
An ATP, but also
It cost me a triphosphate, right? Can we say that's an ATP? That's what it showed you on the previous slide I just showed you. It says ATP, but it's actually a UTP. It means the same thing to us. To make this molecule right here from a glucose molecule cost me not 1, but 2 high-energy phosphates. This is the building block of a glycogen molecule. This is the activated form of this. What's going to happen is this oxygen is going to react with carbon number 4 of a growing chain, making an alpha 1,4 linkage. Remember what that looks like, all right? Which is what glycogen mostly is. It also has a number of 1,6 linkages. Those branch points simply make more ends where I can build glucose molecules and also break them off of, make glycogen molecules. and also break them off of glycogen molecules to make them available for those cells that need glucose. The process of making a glucose molecule from a glucose molecule into glycogen costs me not one, but two high-energy phosphates. The first one's when I make glucose 6-phosphate. The second one, when I do this reaction right here, those phosphates don't show up on the glycogen molecule, but I still need them to make it, all right? Which is why you should have, from glucose 1-phosphate to glycogen, an ATP is being used in that process. And you can put in parentheses UTP to make UDP or ADP, all right? When I go about breaking that glucose molecule off, it says hydrolysis. It's not. It's phosphorylase, which means what? Instead of using a water molecule, I use a phosphate group. From ATP, no, just a phosphate group. And when I take that glucose